don't forget to start. Okay, so for this part, we essentially we wrapped up last week's chapter talking about the four quantum numbers, and the summary was the four quantum numbers were the numbers that were put together in the quantum mechanical model. So we have the quantum mechanical model. Oh, give me just a moment. I forgot my water. Yeah. In the quantum mechanical model, and these numbers are used to pretty much locate the electron. Now, the ultimate goal is we want to know where the electron is. We don't really care about the orbital. It just so happens that the electron is inside the orbital. So the first three quantum numbers help us locate the orbital. Locate orbital, and if we locate the orbital, we essentially located the electrons, because the electrons do not live in the atom naked. They usually are found in orbitals. The first three quantum numbers are your energy level N, your sublevel L, and then your specific shape M sub S. And these together help you figure out the orbital. Okay, and then of course we have the fourth quantum number. The fourth quantum number that helps you to determine the spin of the electron. So what I want to do here is, before I continue, I was trying to skim over this when you showed up. Let's look at the homework, because I want to make sure that we're not going deeper than necessary, that we're not going into sections that you will not be held responsible for. So I'm looking over this, just skimming over the questions here. You're supposed to let's see, they're giving you the radiation for microwave, for infrared, and then, oh, you're comparing the frequencies to the speed. Okay, I see. So that's something completely different. And then here you're answering questions about the electromagnetic radiation, and when you go through these questions here, you have to compare the color with the wavelength. Also a different kind of question. Same thing. So this is about the first third of this chapter. We have Bohr's model here, so we'll go through that. So the questions I'm asking about are about the orbitals. Here they're asking you questions about the different orbitals, the S, the P, the D. They're asking nothing about the F. Let me see. They're asking nothing about the M sub S. So I will look at this last one here, because I don't think they're asking anything about the M sub S. Okay, since they ask nothing about the M sub S, I'm going to go ahead and move on. I won't really even define what it is. So over here, they are relating the energy level, the number of orbitals in the energy level, the sub-level of the energy level, comparing the energy level with the sub-level, and the number of orbitals of each type, which this goes with that, and the maximum number of electrons. So, okay. So, since we're going over this holistically, going back over here, I won't even spend more time explaining what this is. When you go if you choose to go the majors class, we will spend time over there talking about what this fourth quantum number is. But just FYI, since we are here, the fourth quantum number does tell you about the electron spin. The electron can have two possible spins. One is the up spin, the other one is the down spin. So this fourth quantum number has two possible values, plus 1/2, negative 1/2. But once again, I just happened to tell you about it since I started talking about it. We won't do anything with this in this section right here. So we're moving on. Once we have discussed the four quantum numbers, we're now going to take the four quantum numbers and apply it to the electronic configuration and periodic table. So the idea is, four quantum numbers provide you information about the individual electron. Individual electron. So for my morning class, I told them it would be like you were hired by a company to be a hotel manager, and then it was your job to then let people know. Well, it was your job to place people in rooms. If you're placing people in rooms, the rooms, based on this analogy, will be the orbitals, and then the people will be the electrons, and then you go by those rules. in one room. You can have an empty room. The room may have one guest, or the room may have two guests, according to the rules that we're going to be looking at. You will use four quantum numbers to decide how to place the individual electron or the individual guest. Versus electronic configuration deals with a holistic view of the electrons in the sublevel. So right here, holistic view of electrons in sublevels. Okay? So if you're not familiar with this terminology yet, I'm going to use the analogy I just used to build up on this idea here. Once again, back to you being a hotel manager. If you're dealing with four quantum numbers, you're dealing with individual guests. Okay, where is your guest? You have one guest. Where is your guest? What floor is your guest? You can say the guest is on the first floor. Okay, what room number is your guest? You say where your guest is. What wing is the guest? So providing somebody with information about your guest based on the floor number of the hotel, the wing of the hotel, the room number of the hotel will be like the four quantum numbers. Electronic configuration approaches the same idea but holistic view. This time we're looking at not just one electron but groups of electrons. And this time we are placing these groups of electrons not just in one room or one orbital, we are placing them in sublevels. Okay, remember sublevel is different from the energy level. Sublevel is a little bit more complex than just the energy level. So just in case you have a question about that, the sublevel is like taking one energy level and then splitting into different parts. So let me see if I can show you a picture of this. Let's say this is energy level 2. Let me go with energy level 3 because there's more sub levels in energy level 3. We have 3 sub levels in energy level 3. So I'll show that one instead. So let's say this is energy level 3. Energy level. The energy level actually splits into 3 sub levels. One of them is 3s. The other one is 3p. The other one is 3d. So instead of having a continuous energy level like this, we have the same energy level being split into three different segments. So these 3 segments of the whole energy level are called the sublevels. And essentially, if you took all the sublevels and connected them, you will get the energy level you started off with. Okay? So the energy level gets split into 3 parts. They're not equal parts, but these parts are called the sublevel. So we are trying to look at the electrons as we distribute them in the different sublevels. So we're told here, electron configuration is the ground state distribution, right? You're placing the electrons among the orbitals of these species. The orbitals will be on the sublevel, the different sublevels. Okay? The rules that guide assignment of electrons to orbitals. Number 1. At ground state, the electrons fill the lowest energy orbital available. No orbital can have more than 2 electrons. So here's the thing. We're kind of getting the shotgun version of what's going on. Okay? There are rules in how you will assign electrons in the different sublevels. Okay? And we're being told here, I started with the sublevel at energy level 3. There's another sublevel at energy level 2 that usually just has 2 sublevels. That will be 2s and 2p. We also have one sublevel at energy level 1 that just has 1s. So we're being told, when you're trying to decide where do I start, where do I place my electrons, we're being told here, number 1, when you are in ground state, fill the lowest energy level orbital available first before you start filling the other ones. Back to the hotel analogy, it would be like your boss telling you, as manager, when we have guests come in, make sure the rooms on the first floor are full first, and then when the rooms on the first floor are full, then you can go to other floors. Okay? So we start with the lowest energy level orbitals, the orbitals here being like the rooms, and then the sub-level being the wings on those rooms, like different areas of the same floor, different areas, the S area, the P area, the D area, all the same floor, the sub-levels. And then you're being told no orbital can have more than 2 electrons. Back to the hotel analogy. As the manager, you're being told you cannot have more than 2 guests per room, right? So using those rules, when we're starting to assign electrons in the orbitals, we have to remember these rules. This first rule here was put together by a scientist called Aufbau. The second one here was put together by a scientist called Pauli. So there are different scientists that came up with these rules. Arrangement of electrons by quantum model is the basis for the allocation of electrons in the periodic table. So they're telling you this. For us to know what sub-level, like what section, what wing within the same floor for us to go from the smallest energy level to the highest energy level, we will use this periodic table here as a guide. If you remove this part here that belongs to helium and put it right next here, the order is to go from left to right and then go the next level from left to right, left to right, and you go like that from left to right, lower, left to right, next level, left to right, next level. Okay, so what I'm going to do here to illustrate what I'm trying to show you guys here, we're going from left to right. I'm going to write the sub levels as we go from left to right. Remember, the sub level is the sections of the energy level spread throughout the part of the periodic table. So please notice right here, this first sub-level is labeled 1s. We mentioned this before. This is called the S block, right? The S block starts off at energy level 1. So this is 1s here. Next, below that, 2s. We have 3s, we have 4s, we have 5s, we have 6s, we have 7s. When we get to the P block, the green region right here, the lowest level possible is, you can't count this because technically that belongs to S. The lowest level possible here, the energy level 2. So we have 2p, we have 3p, we have 4p, we have 5p, we have 6p, and technically we have a 7p here, but 7p is missing. Okay. When we come to the D block, what is this? Purple color? Let's call it purple. The D block, the lowest level of the D block, this is like the different wing, right, of the same hotel. The lowest level in the D block is 3D. So we start with 3D. Remember, 1S is the lowest here. 2P is the lowest in the green. Now we start with 3 here. And if you skip over and go to this part here, the lowest level starts with 4. Okay? And as you're going down the row, like going from one floor to another, the energy level increases by 1. So we have 3D, 4D, 5D, 6D. Then here we start with 4F and we end with 5F. Okay? So once we see all this, we have seen this before, we're now going to be arranging these sub-levels, the sections within the same floor. We're going to be arranging these according to increasing energy level. Once again, go from left. So I'm going to write down up here. I start with 1S first, right? And let me I'm trying to make sure y'all can follow where my eyes are. So we're on the same page, so to say. Once again, for the purposes of this, move my 1S over here. So I'm starting with 1S first. This part here, that's done. And there's nothing on the right because it's now on the left. Then I go off to 2S. 2S comes next. Then from that, I move over to 2P. 2P comes next. Then I go the third row, call the third period, down to 3S. After that, I go to the right to 3P. After that, I go to the left to 4S, right? After 4S, I go to the middle part, the purple part. It's now 3D. After that, 4P. So hopefully you can, I said 4P and I wrote 4D, right? 4P. Hopefully you can see what I'm doing, right? What comes after 4P? Can y'all see? Right here. After I'm done with 4P, what level comes next? Can you write that in the chat? I want to
Oh,
make sure you all understand. Yes? Or you can say it.
oh, 5S.
5S. Very good. I said 5S. What do we have?
Oh, 5D.
Are you
Or
looking
40,
at?
40, 40, sorry.
Yeah, next to it. You want to go? Yeah, exactly. So the other class was
Admittedly,
like,
I kind
this
of
is
like had like an
good.
overlap thing. I read 5D
Right.
first,
The
or
other class was
3.
accusing me of tricking them. I'm like, I'm not tricking you. You're making assumptions. Just read from left to right. Yeah, after 5S, 4D.
Yeah.
And then after 4D, you see what comes next. You read to the right.
5P.
5P. Right. Okay, so here's the tricky part for this one here. They didn't show you this, but this is a little detour over here. When you're done with 6S, you have to come down here. And then we're done with 4S, you have to come back up here. So it's kind of like a two-way thing, like a detour. So we have 5P, right? After 5P, what comes next?
Oh, 5. Okay, so that's 6S.
6S. After 6S, what do you think comes next? We're not going straight to 5D. We're actually detouring down here. So what do you think comes
Right.
next after 6S?
Yeah. 4F.
4F. Very good. So we detour all the way down here. Come back, come back, come back to this. So what comes next?
5D.
5D. Then you keep going, keep going, keep going to this region right here, and then we're back to 6P. Very good. So essentially, that's what we're going to be doing with the sublevels, right? The sublevels have limits, though. Different sublevels have different orbitals, and therefore different number of orbitals, and therefore different capacities for electrons. I'm now going to use the periodic table model we have here to as an anchor to help us determine the number of orbitals we have for the s. Okay, so you see right here, I'm focusing only on the s's, right? The other one s belongs here, once again erasing that. So in general, the s's max s's have one orbital, so I'm drawing the orbital here, and the s's have got 2 electrons max. So the s's have one orbital, and if the orbital is completely full, it has 2 electrons. So I'm going to go through and show you all the s's. This 1s has one orbital. This second 2s level has one orbital. The 3s level, one orbital. So the boxes I'm drawing around here actually represent orbitals. Another orbital, another orbital, another orbital. So regardless of what energy level the s is, as long as it's an s block element, it tends to have one orbital, and each orbital has a max of 2 electrons. Okay? And then for this part, for the p, I'm going to draw the boxes around the p orbitals of that same sublevel. So I'm looking at 2p right now here. You see the divisions here. Go ahead and draw a box around 2. So I have, this is one orbital, this is the second orbital, this is the third orbital. So going back to what we discussed last week, we had 3 different shapes of the p orbital: px, py, pz, the 3 different p's I showed you last time. Each of them will make up one of the orbitals. So the p sublevels tend to have 3 orbitals. So 1, 2, 3 for the 3p. 1, 2, 3 for the 4p. So all p sublevels have 3 orbitals. Okay? So if I'm going to make a little chart, a summary right here, instead of saying all, I should say each. Each S sublevel has one orbital. So once again, using the analogy, it would be like AKA each S wing has one room. So maybe this could be the suite section of the hotel. I recently went to a hotel and they had a little cove area where the rooms were bigger. You see one door and the rest of the area around it is a wall. So you're thinking to yourself, though I may not see what's behind the door, this may be the suite section of the hotel, right? Where they have those big rooms that look like apartments and you pay lots of money for it. So the S sublevel, the area where the S sublevel is, usually only has one orbital. Okay, so S has one orbital, and then the maximum electrons is 2. Okay, so using the same idea, each P sublevel has 3 orbitals. That's just how they're arranged. So P sublevel, 3 orbitals. Since each orbital can hold 2 electrons maximum, max electrons equal 6, right? Because each orbital, like her room, can hold maximum of 2 electrons. Okay, so we're moving on. We're moving on up. D, back to the picture here. I was trying to use the periodic table to show you how you can use the periodic table to help you with this. Draw a box here, draw a box here, box here, box here. These are ugly boxes, I do admit. They are not very good looking boxes. But I have 1, 2, 3, 4, 5. I have 5 boxes. That means the 3D sublevel has 5 orbitals. And if you place electrons in here, you end up with 10 electrons. So with my list, each D sub level has 5 orbitals with a max of 10 electrons. Okay, so it should continue right here. Based on the trend, we should be able to get 7 down here. Let's see, 1, 2, 3, 4, 5, 6, 7. 7 bad boxes, but we get here 7 orbitals, and when they're all full, they have 14 electrons. Okay, so knowing this, we can now start working on the electronic configuration. When you write the configuration, this is the format. They gave you the element, such as hydrogen, to tell you the number of electrons it has, 1. Remember, the order is to start from the bottommost. Start from 1s. Fill that out. What's the maximum capacity for s's? What did we say right here? Oh, 2. Okay. So we'll start like that. And we'll go in order so that it's at least you can follow along, right? You write the element given to you, you write the number of electrons, the symbol of the electrons, and then you start writing the sublevels. And the superscript will give you the number of electrons in that wing on. So remember that the sublevel is the wing on the floor, because the floor is the energy level. The sublevel tells you the maximum number of electrons placed in that corner, the sublevel. Okay, remember, S's max out at 2, P's max out at 6, D's max out at 10, F's max out at 14. So you want to make sure, regardless of what S you're working with, you can't go beyond 2. And before you move to the next sublevel, you have to make sure that that sublevel you're working with is full. Okay? So what I'm going to do here, they're showing you different configurations. Let me go ahead and pull the one I just copied over. Or I'll just use it right here. I'll come back and look at that. Let's practice a few. So I'll give you a couple of elements here, and then you will tell me what comes first. So let me select some. I'll start with the easier one. I'll start with lithium first. So we'll start with this one here first. And then we'll go with the configuration for phosphorus. Then we'll do calcium. And then we'll do copper. I'll keep it simple, we get to practice, and then, we work this out. Okay, so what I'm going to do, even though I've written these down here, I'm going to write the configuration up here so you guys can follow along with the periodic table I'm using, because I feel like it worked better with my other class this way. Okay, so what I want you guys to do, either say it out to me or type it here I would like for you guys to participate. Let me know what sub-levels I put my electrons in. I'm going to start off with lithium. Lithium only starts off with 3 electrons. I'm trying to place the 3 electrons in the sub-level based on the rules they told me, which would be my electronic configuration. I'm trying to write the electronic configuration for lithium. What do I start with? What level do I start filling? You start with this one here. Okay? So move helium over here. And essentially, you start off with 1s. So remember, this is a 1s sublevel. And I'm going to zoom in so y'all can see. The 1s sublevel houses the first and the second electron. So I'm just showing you where the electrons are. So I'm going to write here 1s, and I place 2 electrons here. But I said lithium has 3 electrons. So where is my third electron? The third electron happens to be in the same location as the lithium element in the periodic table. The third electron happens to be right here. So what's the name of that sublevel? 2s. How many electrons am I placing on the 2s sublevel? Just 1, right? Because when you take the subscript and you add them, you get that there's a total of 2 plus 1 electrons in lithium. The first 2 are in the 1s sublevel. The last one is in the 2s sublevel. You see the labels in here in yellow? So I'm going to help you guys with the first couple. Let me pick another one. Let's work on, what did I pick down here? We did lithium. Let's work on carbon next. So let me actually draw a box instead of a circle. Let's work on carbon. Then for the other ones, I want you to tell me the sub-levels and the number of electrons I place in there, okay? As we get more comfortable. I'm going to start from scratch over here, so I'm going to erase this. Once again, bring the helium electron right here. Please notice where the elements are corresponds with the electron. Electron number 1, this is where it belongs, or this is where its location is. Electron number 2 is right here. Electron number 3 is here. Electron number 4, and so on and so forth. We're trying to deal with carbon. Carbon has got 6 electrons. We're trying to place all 6 electrons in the sublevel based on the electron configuration rules, right? So the first sublevel that ever gets filled is this one. What is its name? It's written right here in this table. 1s sublevel. Okay. I have 6 electrons to place in the available sublevels. How many can I place in the 1s sublevel? Well, only 2. The first electron, the second electron. So I put 2 here. Okay. But I have 4 more electrons to place. I have electron 3, 4, 5, 6. So what do? Well, put electron 3 and 4 where they normally go, which is right here. It says 3 and 4, right? What is this sublevel called? It's called 2s sublevel. So how many electrons am I placing there? 2. I place the third electron and the fourth electron in the 2s sublevels. I'm just reading from here. Okay, I have 2 more electrons though that I haven't placed. So since I'm done with this level, now I have to go to the right. I'm trying to place my 5th and 6th electron. Well, my 5th and 6th electron live in this sublevel right here, this whole sublevel. But I'm not going to use all of this section right here since I only have 2 electrons left. I'll say in the 2p sublevel, the name of this sublevel, I'm only going to place 2 electrons in there. I can't say I'm going to place 1, 2, 3, 4, 5, 6 because I only have 2 electrons left. And please notice, the number of electrons I place in the 2p sublevel land me on where carbon is. I place 1 electron here, 1 electron here, and it corresponds, it matches with where carbon is located. Okay? Are you guys ready to be a little bit more involved in this process? I say yes. Let's do it.
Sure.
I like your attitude. Yeah, let's do this. Okay, so Y'all help me write the configuration for, let's do fluorine. Fluorine is one of those famous elements that's just being talked about here and there.
Okay, so
So fluorine has 9 electrons. Let's do this.
So with that, never mind. Sorry, I'll let you talk now.
Yeah, no, you're telling me. I'm gonna be listening to what you're saying. Uh-huh. Where do I place the first 2 electrons? On what sublevel?
2s. Well, I guess the first ones are on 1s. I guess so.
You have to do this one first. Right, that's the rule. Aufbau's rule says start from the top left. He didn't say that, I'm just paraphrasing. Start here. So 1s first. And I placed 2 here. Okay, now I have 7 left, right? I mean, correct. I have 7 left remaining. Okay,
Yeah.
so this section now is now already full. Where do I go next?
2s.
2s. This is next, right? And how many do I place there?
Just 2.
2, right. Make sure each level is maxed out before you move on, right? So this is now full. 2. Now where do I go?
Okay, so now you can go to 2p.
Yeah, so going from left to right,
right?
So now we go to the 2p wing right here. Now the 2p wing, I have a lot of room, but how many can I place in the 2p wing? Or
so because
sublevel?
you're going to 9, you can place 5 of them.
Very good. We're going to 9, right? I've already placed 4 electrons. I only have 5. So 1, 2, 3, 4, 5, which matches with the element I was trying to place in the first place. So at the 2p level, I only place 5 because that's all I have left. And the configuration, the last position, matches with the element you were trying to place in the very first place. Right. Very good. Yay. Now let's get to the interesting one. So I'm going to erase this. It was hard to come by this periodic table that somebody made, whoever it was, thank you. But they made it, yeah, because the ones that I see online most of the time when the sublevels are there, the elements are not on there. So then you're looking for the elements. Whoops, wrong thing. Okay, so where was I? We did that one. Let's do the ones that have this. Let's do phosphorus. So phosphorus, once again, we'll put helium here. Okay, phosphorus is this one here. So we're going to go until we get to this element. Okay, phosphorus has 15 electrons that have to be distributed. Let's go ahead. Where the first 2 go?
Okay, so 1s again?
1s2. Okay, so I'm done with this. Next.
2s2.
2s2. I'm done with these.
And then you do 2p6.
Very good. We're going to use all of this. We'll keep going until we get to that. We're maxing everything out until we get to this level right here, right?
And that's 10 so far.
The what?
Oh, I just want to make sure how many electrons we are using currently. So
okay,
I said
yeah.
we have 10,
2p6 right? Means we have used 10, right? We have how many more to place? 5. Okay. Okay, so now I'm right here. This is where I am. Okay, what do I do?
3s? Yeah.
Okay, so we're going to fill 3s with 2, right?
Right.
Okay. Now I'm here.
Okay, now so we're on 3p. So you have 3 left to give.
Right. So you see, I'm not even doing the math. The math is good. It's a good way to check. But since I drew a box around this, we stop at the element we're trying to place in the first place. So we can't stop before it or go beyond it. We stop at the element. So in the 3p sublevel, we're going to use 1, 2, 3 boxes. Then you can count to verify, right? 2, 2, 6, 10, 2, 3, 15. Yeah. Okay, you guys are getting this. Okay, let's do one with the other ones. Where's the other one? Because once we do the configuration, then we can do the other things from here on. So we did this one. Oh, calcium right here. So now we're going until we get to this one here, and then we'll stop. Did I select some other interesting ones? You know what? Forget calcium. Let's do bromine. Because I'm like, did I really? Let's do bromine. Bromine is more interesting than calcium. I want us to cross the D block. So I'm going to select bromine. Okay. So we're going to do bromine. Do not be afraid. The same process we learned. Br has 35 electrons. Okay. Where did the first two go? Where all first two go, right? Which is where?
1s.
1s2, right. And in doing this, you realize the first two electrons, regardless of the element, occupy the same location, or they have the same address, right? So 1s2. And
Right.
then what's next?
And
Right
then
here.
2s. 2.
Oops. Okay. 2, 2.
And then
So this is done. This is done. Then where do we go from here? This is
2p6.
2p6, right? 2p6. Now this level is full. What's
Okay.
next?
What's in 3s2?
3s2. 3s2. Okay, now this is full, so we go to the right.
Okay. And then 3p6.
3p6. Yes, sir. 3p6. Now that level is full. We go here.
4s2.
4s2. Then where do we go next?
And then 3d. Okay.
Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, 10. Sorry. Yeah.
Okay. Yeah, okay.
3d10. Remember, D has got 5 orbitals times 2, 10. 3d10. Okay. So this whole section is now full. So we move to the right. What's left? I mean, not what is left over?
Okay, so we're at 4p. We have 5 electrons.
1, 2, 3, 4, 5. Yep. 1, 2, 3, 4, 5. So now 4p5. Yeah. Then I had one more. That one more was going to be copper. Of course, copper, we kind of stop along the way. So you see how the first few. So once you get the hang of it, it's not that bad, right?
Yeah.
Okay. Now we're going to stop at where copper is. Okay, let's do this. So we start from the beginning. Oh, I need to erase this. Erase this. Okay, we're working with copper. Copper has 29 electrons, copper. So the first two go where?
1s2.
Yeah, 1s2.
2s2.
2s2.
2p6. Yeah.
2p6. Max everything out.
Oh yeah. And then 3s2.
3s2.
3p6.
3p6.
4s2.
4s2.
Okay, and of course, okay, one more. So it's 3d9.
3d9. Yes, sir. 3d9. Yeah. If somebody just asked me to do this from my head, I go like, give me a moment. But when you use the periodic table, it's so much easier, right? You're just following along, right? Because
Yeah.
scientists did arrange the elements so that it works out. It's not as simple as it appears. It did actually take some rearranging to make sure. And these numbers, they came to them through experiments. So it wasn't just something that they made up, but it was experimental, determined experimentally. Okay, so y'all know how to write the configuration, locate the element in the periodic table, identify and write the electron configuration of its highest occupied energy level. To the left of what is written, list the lower energy sublevels in order of increasing energy. So when we're going from 1s to 2s, we're doing all of these. For each filled lower energy sublevel, write as a superscript the number of electrons that fill that sublevel. So we were writing the sublevel numbers and then the number of electrons in those sublevels. Confirm that the total number of electrons, the superscript, is the same as the atomic number. So we were doing that in the process, okay? Now, there are some exceptions and interruptions that we're not going to be working on right here. We keep it simple with you guys. So they're saying here, write the configuration for chlorine. What I'm going to do right now is instead of doing the whole thing like they're doing, the whole configuration, I want to kill two birds with one stone. They're showing us two different configurations for chlorine right here. What I call the full configuration, showing you every sub-level ever that chlorine actually fills, versus the one on the right, which is the shorthand. Okay, here's the thing, okay? Chemists work very hard. Okay, I'm not advocating for other scientists because I don't really know them. Like I know chemists work very hard. It's a lot of hard work to learn all this stuff, do experiments. So they get tired of writing a lot of things out. Plus, when you're working very hard and you get tired, the chances of making errors are very high. So we have the complete configuration, and then we have the noble gas core configuration. This is a shorthand. So depending on what the question is asking you, you can provide the full configuration that shows all the electrons in the sublevel, or you can provide the shorthand configuration depending on what is being asked to you in the question. So what I'm going to do here is I want to go ahead and do the shorthand configuration, but let me do the one for the elements we just worked on. So since we did the configuration already, I just realized right now I went ahead and erased them. That's okay. We will do the shorthand configuration, and I think it's just a lot easier for me to write it up here. Y'all see that? So let me go ahead and let's see. This is what? Lithium, potassium, bromine, and copper. So we're going to do the shorthand configuration, and I forget what I'm doing right here. Because it's so much easier for me to write it up here than to go back and forth and back and forth. Oh, I hope this is not freezing again. Don't freeze. Don't freeze on me. Okay. So let me do this for the first one. For lithium, I'll do the quick configuration. The full configuration is 1s2. Oh, no. Okay. 1s2, 2, 2s1. Okay. Let me go ahead and move this to the bottom so we can see how the full configuration is different from the shorthand configuration. Okay, the shorthand right here is going to be, so with the shorthand, there is a format to it. You have an element that you place inside brackets. The element that's inside the bracket is a group 8 element. So I'm going to write here group 8 element. This is your group 8, the noble gas elements. They get placed inside the bracket or the parentheses. And then you fill in the missing configurations until you get to the element. So what I mean by that is, let me go ahead and show you guys the shorthand configuration for lithium after doing the longhand configuration. For this one here, select a group 8 element. This is group 8 that has the number of electrons very close to lithium, but not more than lithium. So I look at my lithium. Lithium has got 3 electrons. The noble gas element that has electron number close to 3 is helium. So what I'm going to do here is I'm going to say, okay, helium. Oh, what did I do?
Oh, so you're the one that's closest to.
Closest to, but not over. So helium will be my element that qualifies, right? So I'll put in here, open brackets, helium. And then remember, helium the atom is 2 electrons. Helium the atom has 2 electrons. So when I place helium inside the bracket, I am essentially saying that helium takes care of 2 electrons. So the number of
So,
electrons that I have to, yes.
oh, sorry to like kind of like skip ahead a little bit. So when we did bromine, would that be argon? Ar
Argon,
or
yes, you pick argon. For bromine, argon will be the best one. You can't pick krypton, even though it seems a lot closer. Krypton has got more electrons than bromine, so you have to pick the noble gas
the
before it, not the one after it. Right.
okay.
And then you fill in the missing configurations until you get to the element. So after helium, I have one more electron to place. So I place this one here. It's going to be this level where lithium is 2s1. This is a shorthand configuration of lithium. So I'm going to write it right here. Shorthand 2, oops, hold on a second. I forgot the helium. Helium 2s1. The next one is what? Phosphorus. I write phosphorus right here. Let me write the longhand for phosphorus real quick. Phosphorus, this one has 3 electrons. Phosphorus has 15 electrons. So we have 1s2, 2s2, 2p6, 3s2, 3p3. Okay, so we already did this before. Now we're doing the shorthand for phosphorus. So that's the part I want us to do together. This is the new information. So for phosphorus, which happens to be right here, once again, starting from, we're trying to place 15 electrons. It's a shorthand, right? So we don't start from the beginning this time. We start from here. Put neon in the bracket, correct? And neon takes care of 10 of the available 15 electrons. What do I write after neon? From neon to phosphorus, what comes next after neon? You want to fill in this
Oh,
sublevel.
okay? Oh, you do three. Sorry.
Okay,
Three.
yeah. 3s2, right? And then we get to this level here, 3p, but you only fill 1, 2, 3, 3. So the shorthand for phosphorus is neon, 3s2, 3p3. This is a shorthand. And it makes more sense as you get into larger elements because then you can see how much less you have to write. Bromine has what, 35 electrons? So let's see what bromine is going to show us here. Oh, let me do the regular configuration for bromine. Where is bromine?
Okay, so you do four, okay, so four, okay, 4s
Okay,
3.
hold on. This thing has frozen. You see, it's not. Oh, come on, iPad.
And then
Yeah, hold on.
E.
I don't know if I'm writing too hard. That happens to it sometimes where it just. Oh, there, it's working again. Okay, you were saying what? The shorthand? Are you talking about bromine?
Yeah. So it'd be helium 4s2. Then
For bromine?
am I the wrong? Am I looking at the wrong one? Okay. Okay. Sorry.
You
Oh,
can't do
okay.
helium. Helium is all the way up
Oh, no,
here.
not helium. My bad. Sorry.
You
Argon.
mean AR, argon?
Yeah, yeah. Yeah,
Okay,
argon.
this
Yeah.
is the best selection right here. Okay, so I'm going to do the shorthand here.
Otherwise,
So for bromine, you can do AR. AR takes care of 18. That works? Okay. Okay, now you tell me from AR, how many sublevels do we fill until we get to BR?
how many we have three
Yeah.
to deal with?
Okay, so which are they after
Oh,
AR?
4s2.
4S, we're going to fill this one. Hold on a second. Let me get caught up with you. 4S2, and then that's done. Then what comes next?
And then 3d10.
Right, then you do 3D10. So go ahead and fill this part here. 4S2, 3D10, and then keep going.
Okay, and then we're at 5 electrons, so 4p5.
4P5. Right, in the 4P sublevel, we only need 5. The 4P sublevel, we just need 5. Okay, very good. Then we have one more. Copper. Copper has what, 27 electrons? Is that what it had? No, 29. That's cobalt. So let's do the shorthand for copper.
That one.
Copper is right here. So what noble gas element do you want to use as the core of copper?
Okay. Oh, copper. Okay. Also,
Okay, I agree. AR is the best choice. Taking care of 18. From AR, where do we go next? We have to keep going until we. So this one is where we start. We're starting from here now, right? And then, what sublevels do we fill until we get to copper?
okay, and then we're at 4s.
4S, you fill these two. Okay, hold on. AR 4S2. And then after that, what do we do? So this is now full.
Yeah, it's not full, so it's 3D9.
Okay, you go to 3D level, and 3D level can only fill 9. Very good. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. The 3D level, we can't fill the whole thing. It's just going to be 3D 9. So, I mean, of course, you have the full configuration here. I won't even write that one. So here's the thing, though. Once you do the two configurations, there's something here that they're trying to show you. I forget. Wait, let me see. The group number. I'm trying to make sure I cover it as we're talking about it. Okay, yeah. So we're told here we can then use the configuration to figure out the valence electrons. So the valence electrons, these are the outermost electrons of the atom. So we recognize that atoms have a bunch of electrons. We don't care about the ones that are close to the nucleus. We can't even access those. We care about the ones that are very close to the surface of the atoms. These are called the valence electrons. Compared to the nucleus, it would be like the nosebleed section, right? They're further away, so far away from the nucleus, these valence electrons. These tend to have the highest energy S and P electrons. So we're told here, highest energy S and P electrons in an atom, which determine the bonding character of the element. So we're told here, the valence electrons, that's the different way they chose to say it, the valence electrons will tell us about the outermost electrons, and therefore they'll tell us about the bonding behavior of the element. Example, phosphorus has this configuration. So they wrote us a whole configuration for phosphorus. The highest occupied energy level is 3. Please notice, when you have this sub-level annotation, these numbers here, the ones I'm highlighting in red, these are your energy levels. The big number. These are your energy levels. So that's the one I was relating to floors versus the sections on the floor or the wings on the floor. So you have energy level 1, energy level 2, energy level 3. They're telling you the highest occupied energy level is 3. You can see that here. These are the highest. We don't have 4. 1 is completely full. 2 is full, but the highest level occupied is 3. There are 2 S electrons and 2 P electrons. Oh, this is a typo. This is supposed to be 3. There are 2 S electrons and 3 P electrons, a total of 5 valence electrons. What we're trying to say here is when you find the highest energy level and you add the superscript, the total of the superscript tells you the number of electrons in the highest energy level. So here's the idea. Electrons in the highest energy level are valence electrons. The electrons in the higher energy level tend to be the ones that are far away from the nucleus. Going back to Bohr's model, just in case you're wondering, Bohr's model said you had a nucleus, you had different energy levels, and he labeled them N is 1, N is 2, N is 3, N is 4. So if you have electrons in the highest energy level in the ugly picture I drew here, the electrons will be somewhere here on that row in that highest energy level, which would be N is 4, right? So of course, based on the structure here of phosphorus, there's only 3 energy levels. So you draw 3 rings around the nucleus, and your 5 electrons are on that 3rd energy level, okay? So if you add 2 to 3, then phosphorus has 5 valence electrons, if I can spell. I need to mention one more thing. Please notice the valence electron equal group number. They haven't mentioned it yet, but I'm just telling you right now. The number of valence electrons equal number of, group number. I shouldn't say number of group. Group number. Okay? So while we're here, make sure you write this in your notes. It's a very important concept. This is an important concept, and so this part here. These are all important concepts. Number of valence electrons equal group number. Okay? So you could use the group number to figure out the number of valence electrons. Before we look at this chart right here, I want to go back and look at our periodic table and see, where's my periodic table, the cool one, the one that has the sublevels. Oh, let me add in my own group numbers right here. So I'm going to write my group numbers. This is group 1A. This is 2A, 3A, 4A, 5A, 6A, 7A, 8A. So based on these group numbers here, these group numbers go with the valence electrons. So these elements here all have one valence electron. These here all have two valence electrons. These here all have three valence electrons. We got four valence electrons. We got five. We got six. We got seven. Here it's complicated. The lower ones have 8. This top one has 2. That's why for quantum number, we bring this back up here. Okay? But remember, the S block and the P block have predictable behavior. So we can use their position to guess their group number. That being the case, go back here to this. What table is that? The table is telling you, now, if you find group 1A elements, they usually in group 1, they have one valence electron, the number of valence electron 1. An example here is Na. By the way, the number of valence electrons are also equal to electron dots. Okay? For some reason, as I'm writing electron dots, I suddenly have, I'm not even crazy about this dessert. What do they call it? The colorful dots of the mall ice cream? Sprinkle dots? I don't know. I just had a
Do you mean like Dippin' Dots or something like that?
Dippin'
Or
Dots, yes, those. As I'm writing electron dots, I'm thinking, ooh, it
yeah.
would be nice right now to have some of that stuff. I'm sorry. I just had lunch too right before we came here. Anyway, like Dippin' Dots, right. Anyway, what's his name? The scientist Lewis, he likes using dots to represent electrons. So he shows us symbols called Lewis symbols, where this is the format of the symbol. You have the element name in the middle, whatever the element is, and then you have dots around the element, and the dots represent the number of valence electrons. So we're being shown here, sodium has one dot, and this dot here just tells you sodium is in group 1 and it has one valence electron. You see magnesium right here having 2 dots? Magnesium is in group 2 and it has 2 valence electrons. So you want to make sure you know how to write this out. Know how to write an element, or at least select, because you guys' exam tends to be multiple choice. Select from a list of questions and they tell you, here's an element. Select its correct Lewis structure. You select from the list of, correct number of dots per group. So when you have group 3, we have 3 dots, right? Group 4, 4 dots. Group 5, 5 dots. 6, 6 dots. 7, 7 dots. And they have 8, finally 8 dots. So you want to know how to write that too, because at some point, I think in some of your labs, you would have to write that. So once we do all that, let me see. We've done all of this already. Yes, so the Lewis symbol, once again, you want to know how to write the Lewis symbol. Here they're telling you write the Lewis symbol for the element tellurium. They show it to you right here. Tellurium is in group 6, so you have that symbol. Let me do one that's not here, okay? One that's not already done. I will find my periodic table that I wrote on and then write an electron dot structure right on it. Oh, right here. So let me do one for aluminum. Can I do one for aluminum? Oh, right here. This is aluminum. So aluminum is in group 3, right? So I'm just going to write 3 dots around it. There. Electron dot symbol for aluminum. If you're asked to do one for oxygen, oxygen is in group 6. So put 6 dots around it. You can do left, right, top, bottom. That's 4 dots. Left, bottom. 6 dots. This would be the dot symbol for oxygen, dot symbol for aluminum. Simple enough.
So does it matter where you put the dots? I mean, so like I know like if you have four, you need to have like four all around, you know?
Right. Different
But
books
like
do it differently. Like you can start clockwise, counterclockwise, top and bottom. But for the ones I've seen, and I'm glad you asked that question. For the ones I've seen out there, is usually at least you want to make sure you have one top, bottom, left, right. So it's kind of like to match with the coordinates, right? The x and the y coordinate versus trying to do them diagonal. But if you do them diagonal, like in between 45-degree angle, it's not necessarily wrong. It's just not very popular. It's
okay.
usually like 45 degree angle between the dots, but nobody's gonna, yeah, most of the time with your homework, you're not writing it in. If you're using the simulation thing with the Lewis structures, wherever you drop the dots, as long as the numbers are correct, will be accurate.
Okay, because I noticed like in the table chart that's on the PowerPoint, I
Mm-hmm.
noticed that they put two dots first, and then I
Together,
noticed.
yeah, I have seen some books where they will never do this. Oh my goodness. They're really following the Vesper model or the Vesper rule that says that electrons don't like to spend time together. So that will be drawn like that. Yeah.
Okay, okay, curious.
Yeah. So it all depends. Different books are following the rules. Some books are more strict about the rules. This book is a little bit more casual. Yeah.
Okay,
Other books will not be caught anywhere near this structure right here.
okay,
Yeah. So as long as the homework accepts it, you're fine. But if you go to since we're using electronic homework, the biggest thing here is making sure the homework accepts it. Right. But if you're asking for accuracy, the more popular one is this one here
okay. Gotcha.
versus that. Right. Okay, so let's see. We've done this part here. We have done electron dots. Right. Okay, trend. We're now moving to atomic trend. We've done a lot of dialoguing about the periodic table. We're now moving at atomic trends. So after seeing all this here, we're now told atomic size decreases from left to right on the periodic table. Atomic size is increasing from top to bottom. Okay, and they're telling you the reasons. The reasons is highest occupied principal energy level. Valence electrons occupy higher principal energy levels farther from the nucleus. Okay, let me try to break this down and make this as simple as I can. We're going back to Bohr's model because even though we told Bohr his model was overly simplistic, it didn't explain a lot of things, but when it comes to teaching chemistry, it's a lot easier to teach chemistry from Bohr's model than from quantum mechanical model. So let's use Bohr's model here. He says we have a nucleus that's positive and we have different energy levels. We won't use the term orbit because we concluded that wasn't correct. Okay. Okay, I'm close to the end. Yes. Okay, energy level 1, energy level 2, energy level 3, energy level 4. So I'm using Bohr's model to illustrate the size of the atom, but I'm explaining it from the part of the model that we agree with. We have 4 different energy levels here. And we're being told, bottom line. I'm paraphrasing the words that are being said here. Bottom line. Atomic size. Atomic size is influenced by two major, I should say, I want to say, yeah, situations. Number one, position of valence electron. Okay. I would say number one is the most objective one. Position of valence electron. Number two is the nuclear charge. So if you can figure out the position of the electron, then of the valence electron, not all the electron, the valence electron. So looking at this right here, we have a nucleus in the core. in the center. And your electron can either be on energy level 1, the closest row to the nucleus, energy level 2, energy level 3, or 4 based on this picture. If your valence electron is furthest away from the nucleus, which is where the valence electron is, that will make the size of the atom very big. Imagine you have an atom that is this big right here. Or you have another atom. Let me see if I can copy this. So imagine we're comparing these two atoms, right? The top one and the bottom one. So on the top one, your valence electron, your outermost electron, is an energy level 4. On the bottom one, your outermost electron is an energy level 2. It's obvious. The one on energy level 4 is very, very far away from the nucleus, right? Making this top atom a larger atom. So I use the position of the valence electron to determine the size of the atom, to determine the relative size. The one where the electron is far away from the nucleus, further away, will be larger. By comparison, this one here will be relatively smaller atom. Okay? The number 2 reason is called a nuclear charge. With a nuclear charge, this is when the size of the nuclear charge or the positive charge in the nucleus changes. And so we're being told here, I'm trying to make sure I explain this without, wait, I'm trying to add a page here. Come on. It's frozen again. PowerPoint slide. Okay, I have to wait. When I mess it with it too much, it freezes and then it won't respond. Oh, come on.
Oh, okay. I thought it closed.
Yeah, no, I'm trying to get it to work again. Okay, hold on. Let me just X out of that. No, it's I don't know. Maybe I need to restart my iPad. Oh, there it is. Now it's working. Okay, great. So yeah, you can see the size of the atom, right? Larger atom makes more sense. Smaller atom makes sense. Next one is nuclear charge. So with nuclear charge, to show you that, I'm going to go ahead and add a page here and show you how nuclear charges can be different. The nuclear charge, like the name suggests, is the charge on the nucleus. This rule for comparing nuclear charge works from the left to right in the periodic table. For that reason, to look at comparing nuclear charge, I will look at carbon, nitrogen, oxygen, and fluorine. For these 4 atoms, I'm going to draw a basic Bohr model here, a simple one, so you can see how the nuclear charge is different. Okay, this will be my Bohr model. I'm going to copy this and paste it on all 4. Copy, paste. I should make this a little smaller. And then paste. Okay, this is probably not the best picture, but you get the idea. So this is carbon, nitrogen, oxygen, fluorine. So carbon has how many electrons? Carbon has 6 electrons, nitrogen has 7 electrons, oxygen has 8 electrons, fluorine has 9 electrons. So based on the number of electrons, I'm going to put the positive core here. Because carbon has 6 electrons, its nucleus has to have 6 protons. Nitrogen has 7 electrons, its nucleus will have 7 protons. Oxygen will have a nucleus of 8 protons, and then fluorine will have a nucleus of 9 protons. It has to match the atomic number. Okay, now I'm going to draw in my electrons. This is energy level 1, energy level 2. This is true of all of them. Energy level 1, energy level 2, energy level 1, energy level 2, energy level 1, energy level 2. Okay, so the total number of electrons energy level 1 for carbon, 2 will be here. You probably have seen this old school way of showing the model of the atom based on Bohr's model. And then let's see, two of the six come to energy level one. Then we have four remaining. So we put one, two, three, four, right? For nitrogen, we have two in the middle. And then we have remaining five goes one, two, three, four, five. For oxygen, we have two in the middle, and then we have six remaining from here. One, two, three, four, five, six. For fluorine, we have two in the middle, one, two, energy level one. Then we have how many? Seven remaining. One, two, three, four, five, six, seven. Here's the thing. When you look at the charge of the nucleus from carbon to nitrogen to oxygen to fluorine, notice the nuclear charge increases, right? From carbon to nitrogen to oxygen to fluorine, the nucleus goes from +6 to +7 to +8 to +9. But look at where we are adding the electron. From carbon to nitrogen, the new electron, which I'm going to highlight here, the new electron comes in on the same energy level. From nitrogen to oxygen, the new electron came in on the same energy level. From oxygen to fluorine, the new electron came in on the same energy level. If you look at all of these, because the additional electron is coming on the same energy level, what explains the size here is actually the increasing nuclear charge. As the new electron is coming in, it's actually being drawn by a stronger core each time. The core of the nucleus increases as the positive charge increases. I'm going to write this here so you can see. As the positive charge increases, the core of the nucleus increases. So what does this have to do with size? It actually sucks in all these electrons closer, and it pulls it a lot closer to itself because the nucleus in the middle here is acting like a magnet, pulling in all of these electrons to itself, including the last electron that came in. So as far as attraction power, the one with the greatest positive charge has the greatest attraction power. So of these right here, this will have what we call the greatest nuclear charge. So, long story short, fluorine will be the smallest element. Okay? So, if all the chemistry escaped you, I'm going to give you an analogy that helped me survive chemistry when I was learning this. Since we got to learn chemistry so many years from middle school all the way to college, I had many years to make up new stories that helped. I love to work out. And I've realized that people who work out their core, when they have a strong core, they tend to have a smaller stomach, right? Their midsection is smaller when they work out their core, and their core is tighter and is stronger. So I use that analogy of understanding how working out works, and how the whole core thing works. They say, work out your core, tighten that core. I'm thinking, greatest nuclear charge, right? As the nucleus becomes more positive, the atom gets smaller. Why? The core of the nucleus is able to behave like a magnet and suck everything in the atom inside, kind of like a vacuum, but not really sucking it into nothing. It's just pulling it tighter inside. And so it has a more smaller size of the atom. And that's the idea here. So going back to here, nuclear charge. As the number of protons in the atom increase, the positive charge in the nucleus increases. Valence electrons pull closer to the nucleus, so the atom becomes smaller. Remember, the atom is using the nucleus to pull in all those electrons. As the nucleus becomes more positive, the atom gets smaller. So here's the picture. Ignoring this group right here, fluorine is the smallest atom ever. That means fluorine has a very strong nuclear charge. its core is very strong. And then the picture here, cesium is the largest atom ever. That means cesium does not have a very strong core. Okay, and the valence electron in cesium is very, very far from the nucleus. So let me show you another simplistic way, because I had to survive chemistry, y'all. Okay, just like you guys had to survive chemistry. I'm trying to show you the little fun stories I made up. I figured if you have to go through it, why not make it fun? Why not make it relevant? So when we ask the question, arrange the following elements into increasing size of something, I try to draw my own simple periodic table with fluorine in the top right corner, cesium in the bottom left corner. Fluorine is the smallest, because I struggle with memorizing, and I really try to memorize this stuff, and I'm like, this is so hard. You know how you guys say so sometimes, but y'all are very quiet, so you're not saying anything. That was me. Oh, am I ever going to learn this stuff? Obviously, I learned it, right? Cesium is the largest element. So my mind works better with logic versus just memorizing a bunch of disconnected facts. So once I figured the logic, I was like, oh, I can do logic. Memorizing, So if in the periodic table, you're usually doing a side-by-side comparison, which is called the left to right periodic comparison, or a top and bottom comparison, top to bottom. So here's the thing. Since fluorine is the smallest, if you're going from left to right, starting from the left, going towards the right, for fluorine to be the smallest, we can conclude atomic size decreases. And we're told there's a trend. So you can see here, as you go from left to right, the size gets smaller and smaller and smaller and smaller until you get to fluorine. You can remember that. Any direction, regardless of where you're starting from, as long as you're heading towards fluorine, the size of the atom gets smaller. That has to be true for fluorine to be the smallest. Okay, let's do a different relationship. How about we go from let's go from bottom to top. If we are heading towards fluorine, the same must be true. Size must decrease, right? For fluorine to end up still the smallest. But if we're going away from fluorine, doing the opposite trend, then the size must increase for fluorine to still be the smallest. So what I did, once I'm listening to the teacher and I'm like, wait a minute, she's saying a lot of things, but bottom line, she's saying fluorine is the smallest. So I said, okay, fine. Why not just memorize fluorine is the smallest and then go from there? That's what I did. And later on, I figured cesium was the largest. It took a couple of years to figure that part out. Go figure, right? But yeah, fluorine is the smallest. So if you are moving in a direction away from fluorine, the atoms have to be getting bigger. If you're going towards it, it's getting smaller. Okay? Now that we know that, let's try to apply that in this is the same thing I was saying right here. In the question, it's saying here, referring only to the periodic table, okay, list atomic numbers 15, 16, 33 in order of increasing atomic size. That's a weird question, but we'll do that. Okay, so they want us to place atomic number 15, 16, 33. So the elements in the periodic table are listed from left to right, right? From left to right, according to increasing atomic number. They said refer to periodic table. I don't want this one here. I want the one that has numbers in it. Why make it difficult on yourself? Find the one that has numbers. So I'm going to do that here. Yes. Let me actually see if I can copy this so I don't have to scroll back and forth so much. This periodic table is very helpful. Let me see. Did I copy it? Okay. Let me go back to the one I was using so I don't have to scroll so far back. We are working this problem right here. I'm going to paste. Oh, that's fine. They said 15, 16, and 33. I can find those here. 15, 16. Oh, come on. It's frozen again. I was being so zealous. But 15 will come before 16, right? Let me see if I can delete that again. I will have to reset my when I'm done with you guys. I have to reset this because it's just, yeah, and then they all came back. That's okay. 15, 16. So 15, 16, this is right here. 15, 16, 33. Okay, you can see fluorine is the smallest atom, right? Smallest ever. So that means that anything that's very close to fluorine is very small too. So based on this, which one do you guys think is the smallest? They said compare atomic size 15, oops, 15, 16, and 33. So we're comparing these three here. They didn't say anything about fluorine. I'm just using fluorine as my anchor. I know this is my smallest. So which one do y'all think is of these three, P, S, and AS, which is the smallest? Any takers?
I'm assuming it's sulfur, or is that that's sulfur,
Yeah,
right? Is that
I would say
okay?
sulfur because it's the closest. Anything close to fluorine is really small. So sulfur will be the smallest. And then which would be the largest?
Oh God, I can't remember what it is. AS.
Okay, that's fine. AS would be the largest.
Oh, what is that again?
Yeah, that would be arsenic, right? I think it's
Oh,
arsenic. We have acetine right here. Yeah, arsenic. Okay, largest, smallest. And then that makes the phosphorus the in between, right? This is the one
yeah.
that's furthest away from, yeah. So when they're asking you to arrange elements that way, use the periodic table. Don't make it hard on yourself. Use the periodic table. The one that's close to fluorine is the largest. The one further away is smaller. Okay, let me see. Is there anything relating to that? So I want to go over ionization energy, at least go over that part, and then whatever we have left, we'll cover in the next lesson. Yeah, I want to go over at least the ionization energy, do this trend, and then I'm seeing how much we have left, chemical families. Yeah, the rest of this is not that bad. So let me go over ionization energy because it relates to size, and then the rest we'll cover on Thursday. So on Thursday, I don't necessarily, it won't take me that long to cover the rest because it's not very convoluted. So if you guys have questions about chapter 4 or 5 or this chapter, please bring them then so we can discuss. Okay, that'll be a good time to bring those kind of questions. So ionization energy is the opposite of atomic size. With ionization energy, you as a scientist are trying to remove the electron. So here's the thing. The easiest electron to remove is the one that's furthest away from the nucleus. This is the energy required to remove one electron from a neutral gaseous atom of the element. It increases from left to right in any row of the periodic table, decreases when you're moving down the group. So yeah, with this one here, let me go ahead and show you the little scheme or picture I draw. I draw the same picture we just talked about, atomic size. This is supposed to be a square. I have fluorine right here. I know fluorine is the smallest atom, and then cesium, largest atom. Then I know fluorine, so going towards fluorine, you have increasing atomic size, right? So the ionization energy trend is opposite to atomic size. So what we do here is if atomic size increases to the right, then ionization energy, sorry, it's supposed to be decreasing. I did the opposite, right? Decreasing. So it's like, this is not right. Decreasing atomic size for this to be the smallest. Ionization energy increases as we go from left to right. So the size gets smaller, but the energy required to remove the electron is more. And then as we go from top to bottom, size increases, then ionization energy decreases. Okay? So for this one here, they can give you different questions and they can give you, arrange the following elements according to increased ionization energy. You want to make sure you follow the model to answer the question. Let me see if we do have some questions in here. It'll be a lot easier to go through that. And I won't even go through the reasons here, the nuclear charge. I won't go over that part yet. This is what I just covered. Oh, here. Okay. We're now supposed to arrange B and F and then FClBr. Okay. They didn't make that one very interesting. So B and F. With B and F, we're trying to arrange these elements according to increasing ionization energy. You want to have your periodic table again. B and F. This is B right here. This is N. This is F. You can see B and F is actually arranged according to decreasing size, right? From left to right. This is actually going to be decreased size. Therefore, the way these are arranged is going to be increasing ionization energy. So if they want you to arrange these elements according to increasing ionization energy, you write them in the same way. So since fluorine is going to be the smallest atom, it will require more energy to remove the electron from fluorine. Okay? So for the other question they gave us here, F, Cl, and Br. Wow. It's just like right here. F, Cl, Br. You can see it's arranged like that. In F, Cl, and Br, when you compare the group comparison, you can see Br is going to be large compared to the 3. Therefore, it will have a smaller ionization energy. Let me see if I can make up my own question that is kind of mixed up, because this one here makes things seem so simple. Like everything is going to be arranged like that. Let me find one that's kind of mixing them up. Let's do sulfur, potassium, aluminum, chlorine. Yeah, let's go with that. And fluorine. Let's go with that. Okay, so for these, I would say arrange in order of increasing ionization energy. And this is a list: sulfur, potassium, aluminum, chlorine, and fluorine. And after we do this, we'll be done, because the rest of it is just additional details. So in order of increasing ionization energy, that means make sure the one that has the highest ionization energy should be the one on the right, and then of course the one with the lowest ionization energy should be the one on the left. So what do y'all say? What do I start with? Which has the highest ionization energy? It will
Okay, so
help.
going
Oh,
from up
sorry.
and down. So, oh, sorry. So up and remind me how the relationship between going up and down again. Does that also affect
Yes,
ionization
yes.
energy?
So to help you out visually, let me, what I like to do here, I like to write in or mark the elements we're looking at. So it's not just all in my head, right? Let me mark them to make it easier. We're comparing fluorine, right, with
Yeah.
chlorine,
Yeah.
with aluminum,
Right in the middle.
right, this one here,
Yeah.
with potassium,
All right. So,
with sulfur. So we're looking at these right here. This, and this. So you can at least tell the extreme ones, right? The two extremes. Which one will have the lowest ionization energy? Which one has the highest ionization energy?
okay, so lowest would be potassium, of course.
Okay, it's furthest away from fluorine, right? So that means it's a huge atom. So of course it will be potassium. And then highest,
Fluorine.
fluorine. Okay. So we know the lowest is potassium, highest is fluorine. How do the rest fit in?
Okay, then I'm assuming it'd be chlorine next.
Next to who though? Potassium or fluorine?
Sorry, to fluorine. So put it
Okay.
right before, and then
Mm-hmm.
right before the chlorine will be sulfur,
Mm-hmm.
and then the middle, of course, will be aluminum between the two.
Yep. Because chlorine is just one step away from fluorine. Sulfur is like two steps ish away from fluorine, and then yeah, aluminum is here, and then of course yeah, and that's how you do it. So I try to remix the rules so you guys can see. You're comparing. It's a vertical horizontal comparison, but the one furthest away from fluorine is the one least alike or least like fluorine, right? So when you go over your homework, look at things like that. The rest of this stuff helps you answer certain questions. It's just extra details like this one here. But yeah, and then this one here too. And so I don't think you guys will do much with second ionization energy, but I'll define them quickly. This is just trying to get the second electron out. This one here trying to get the third electron out. You guys don't do much with this in this class. That's more like a majors level class. We don't do much with that. We already did this part here, so we're good on that. When we meet on Thursday, I will start with this slide here. Okay? Bring questions
Oh,
from chapter 4, 5, and 11. Yes, sir.
I was gonna ask. So I remember you mentioned like.
Wait, sorry. There's interference, so I can't hear you.
So one thing I wanted to ask. So I know like Singapore is the highest now, but between.
Wait, wait, hold a second. All of a sudden, you sound so far away. Did you move from your mic?
Hello?
Yeah.
Do I sound alright?
You sound far away, but I'll increase my mic over here. That's okay.
Let me try again. Does it sound better now?
Yes, better.
Okay, I literally had to mute myself and mute myself back on. With the error, I guess.
Okay.
Maybe? Okay, anyway. So so when we're talking about ionization energy,
Uh-huh.
so let's say for example, oxygen versus chlorine. Which one would be higher versus lower against that? Are there one over like left versus down? How would you tell which one's?
Oh, you guys level, they weren't asking anything that complex. You mean oxygen and chlorine? Oh, because I see. Yeah, at your level, they weren't asking anything that complex. It has to do with the size of the atom. So where is the picture I have for the size? I'm trying to show you the picture for the size.
Oh, okay, I
This
see.
one right here. Right.
The
The
chlorine.
easiest way to answer that question is look at the size. So see, fluorine here has an atomic size. They gave you this number. Chlorine is 100. Oxygen is 73. So this is larger than that, right? And you can see right here, this is larger than that. So this will require less energy. This will require more energy.
Okay.
It's
Noted.
just it's the opposite of the numbers you have in this picture, so to say. That would be the easiest
Okay.
way I would advise you, right, to answer that.
Okay. Cool. All I need to know.
Yeah. Other than that, that's it. That's all I have for today. My goal is not to is try to explain without overwhelming. It's a delicate balance with chemistry, but yeah.
Fair enough.
But
Okay.
Thursday, I'm going to be finishing this chapter, and then feel free to come in with questions there, chapter 4, 5, and 11, and yeah, at that point we'll decide what we do next. Okay?
Okay. Cool.
Because I found out your exam is not this weekend; it's the weekend after, which you're
Right.
free to take it this weekend. You're ready for it, because the longer you wait, the more you forget stuff. Information doesn't just build. It's not like fermentation process that gets better with time, right? You have to either study more, or if you're not studying, you're forgetting it. So I was about to say it's like muscles, but kind of like muscles. If you're not working them out, you're losing them. So
True.
yeah. So I guess I'll see you guys on Thursday. Y'all have a nice evening.
You too.
Okay, thank you. Bye.
Bye.